Okay, so today we're going deep on a topic that's pretty fundamental when it comes to how computers manage huge amounts of data. We're talking about B trees.
Right. Yeah.
You sent over this chapter summary, and it looks, well, pretty dense. So our mission today is to really break down B trees, figure out why they're so important, and how they actually work.
Yeah, I think it's easy to overlook stuff like this, but B trees, they're like the backbone of so many systems we use every day.
Yeah.
Like when you search on Google or, do anything with a database.
It's true. I mean, have you ever thought about how quickly Google can search through billions of web pages,
Yeah.
or how your bank can instantly access your account details? It's pretty mind-blowing.
Definitely. And a lot of that speed and efficiency comes down to, yeah, data structures like B trees.
So it's about making things fast, especially when we're talking about data that's too big to fit in your computer's main memory, that RAM.
Exactly. It's all about managing that data efficiently on disk, on those hard drives or SSDs.
Okay, cool. So this chapter summary we have, it's pretty comprehensive, right? We're going to unpack the structure of B trees, the nitty-gritty of adding and removing data, and really get into why they're so good at minimizing those slow trips to the disk drive. That's the key, right?
Yeah, absolutely. I mean, that's the whole point.
So to kick things off, can you give us a high-level view? What exactly is a B tree, and why is it such a big deal in the world of data management?
Okay, so in simple terms, you can think of a B tree as this, self-balancing tree structure.
Hmm.
It's specifically designed for storing data on disk, like we were saying.
Okay, so we're talking about disk, not RAM.
Yeah,
Got it.
right. And you might have heard of other balanced trees, like red-black trees, for example.
Oh, right. Yeah, familiar with those.
Like those B trees also let you do things like searching, inserting, deleting data. And they can do all that pretty quickly in roughly logarithmic time, which is pretty efficient.
Okay, logarithmic time. That's good, right?
Yeah, it basically means the time it takes to do those operations. It doesn't increase drastically, even when you add tons of data. But the real secret sauce with B trees, what makes them so special for disk storage, is their large branching factor.
Branching factor. Okay, explain that a bit more.
Sure. Imagine a typical binary search tree, right? Each node has, at most, two branches, two children. A B tree, on the other hand, can have many, many more children per node. And that right there, that's the key insight. This wide branching, it makes the tree much shorter, much shallower.
Okay, so instead of this tall, skinny tree, it's more like this wide, bushy tree.
Exactly. And that's super important because accessing data on a disk is slow, way slower than accessing it in RAM. So the fewer levels we have to go through, the fewer trips to the disk we need to make. And that means things are way faster overall.
Makes sense. Shorter tree, fewer disk accesses, faster results. Okay, I'm starting to see the logic here. Now let's zoom in a bit. How are these B tree nodes actually structured? What are the building blocks?
All right. So each node in a B tree, let's call it node X, just for reference, it has several components. First, there's this thing called XN. This just tells us how many keys are currently stored in that particular node.
Okay, so it's like a count of the keys in the node.
Right. Then we have the keys themselves, and they're arranged in order, from smallest to largest. So we have x.key1, x.key2, and so on, all the way up to x.key, x.n. That's the last key in that node.
So far, so good. Keys are stored in order within each node. What else?
Now, each node also has this little flag, a Boolean value called x.leaf. And this just tells us whether it's a leaf node or an internal node.
Leaf and internal. What's the difference there?
In a leaf node, that's like the bottom of the tree. They don't have any children, they just hold the data. Internal nodes, on the other hand, they're the ones that guide us down the tree.
Okay, so the internal nodes, they're like the signposts pointing us in the right direction.
Exactly. And to do that, they have pointers to their children. So if an internal node X has x.n keys, it's going to have x.n plus 1 child pointers. We can call them x.c1, x.t2, and so on.
Okay, one more child pointer than the number of keys. That makes sense. Now, how do these keys and pointers actually work together to guide the search?
Well, the keys in an internal node, they act as dividers. They basically tell us what range of keys we'll find if we follow a particular child pointer. Let me try to explain that a bit more clearly.
Yeah, please do.
Okay, so let's say we're looking at an internal node X, and it has these child pointers, x.c1, x.c2, and so on. Now, if we follow pointer x.ci, any key we find in that subtree, it's guaranteed to be within a specific range.
A range defined by the keys in node X, right?
Right. All keys in that subtree will be greater than or equal to the I1 key in X, if that key exists, of course, and less than or equal to the ith key in X.
Got it. So the keys in the internal node, they create these boundaries, these ranges that tell us where to go next. It's like they're saying, hey, if you're looking for a key between these values, take this path.
That's a great way to put it. And because everything's sorted within the nodes and across the subtrees, this whole structure ensures that we can find any key pretty quickly, just like in a regular search tree.
Cool. Okay, so we have this idea of keys dividing the data, guiding the search. You also mentioned earlier that all leaf nodes are at the same depth. Why is that significant?
That's a really important point because it's what keeps the bee tree balanced. Every path from the root of the tree down to any leaf node, it has the exact same length. And this length, that's what we call the height of the tree, denoted as h.
So no matter which path you take, you'll always travel the same number of levels to get to a leaf node.
Exactly.
Yeah.
And this balance is super important for performance because it prevents the tree from getting all skewed and wonky, like, an unbalanced binary search tree can sometimes become.
Right, like when everything ends up on one side and it becomes more like a linked list than a tree.
Exactly. And that would kill our performance, especially for disk access. So this balanced structure in a B tree, it guarantees that our search times stay nice and logarithmic, no matter how much data we add or remove.
Got it. Balance is key for efficiency. Now, the chapter summary introduces this concept of a minimum degree T. Sounds kind of technical. What's the significance of this T value?
Yeah, the minimum degree T, it's a fundamental parameter. It basically sets the rules for how many keys each node can hold, both the minimum and the maximum.
Okay, so it's like a control knob for the density of the tree?
Kind of, yeah. So the rule is this. Any node in the tree, except for maybe the root, that has to have at least T1 keys. And for any internal node, again, except maybe the root, it needs to have at least T children.
Okay, so T to setting the lower bound. What about the root? Why is it special?
The root has a bit more flexibility. If it's not empty, it just needs to have at least one key. It doesn't have to follow that T1 rule.
Okay, interesting. So the root gets a little leeway.
Right. But for all the other nodes, this minimum degree T, it makes sure they're reasonably full. It prevents us from having lots of nodes with just a few keys, which would be inefficient.
It's about making the most of the space in each node, right?
Yeah, exactly. And there's also an upper limit. Every node in a B tree can hold a maximum of 2 T1 keys. And as a consequence, an internal node can have at most 2 T children.
So we have a minimum number of keys and a maximum number of keys, all controlled by this minimum degree T. And when a node hits that upper limit, that 2T1 keys, what do we call it?
We call that a full node. And that concept of a full node, it becomes really important when we talk about how we insert new keys into the B tree.
Okay, full nodes. We'll get to that in a bit. But before we dive into the operations, let's take a step back and talk about why this whole B tree structure is so well suited for disk-based storage. The summary really stresses the performance difference between main memory and disk drives.
Yeah, that's a huge point. Like we mentioned earlier, your computer's main memory, the RAM, that's super fast. The processor can grab data from there almost instantly.
It's like having all the information you need right at your fingertips.
Exactly. But RAM is also pretty expensive, and it's limited in how much data it can hold. Disk drives, on the other hand, like your hard drives or SSDs, they can store way more data.
Right. I mean, terabytes of storage these days, easily.
Yeah, huge amounts. And they're cheaper than RAM, but the trade-off is that they're much, much slower. I mean, we're talking orders of magnitude slower.
Why is such a drastic difference in speed?
It all comes down to the mechanics. With RAM, it's all electronic, very fast. But a disk drive, it has these physical moving parts that are spinning platters and a read-write head that has to physically move to the right spot to access the data.
So it's like having to go find a specific book in a giant library.
Exactly. That physical movement, it takes time. And that's what we call latency. It's the delay before the actual data transfer can even begin.
Okay, so it's the physical limitations of the disk that create this bottleneck.
Right. And because of that latency, accessing individual pieces of data on a disk is just way slower than doing it in RAM.
So how do we deal with that?
Well, to make things more efficient, disk drives don't read or write data one byte at a time. They transfer it in larger chunks, kind of like reading a whole paragraph instead of individual letters.
That makes sense. What are these chunks called?
These chunks are called disk blocks, and they can range in size, typically from 512 bytes to 4096 bytes, or even larger.
Okay, so accessing data from disk happens in these block-size units. How does the B tree structure fit into this picture?
The beauty of a B tree is that it's designed to minimize the number of times we have to go to the disk, those expensive disk read and write operations.
Because those are the slow ones, right?
Exactly. When we're working with data that's stored on disk, The overall performance is often dominated by how many times we have to read from or write to the disk.
So the goal is to minimize those disk operations as much as possible.
Precisely. And B trees do that by trying to keep only a few disk blocks in RAM at any given time. This allows them to manage datasets that are way too big to fit in RAM all at once.
So it's like bringing a small, manageable chunk of data into RAM, working with it there, and then potentially writing it back, all while minimizing the total number of those slow disk operations.
Exactly. And that's where the large branching factor that we talked about earlier comes in. By packing lots of keys and child pointers into a single node and sizing that node to match the size of a disk block, a B tree can store a lot of information in one disk read.
So each trip to the disk is more worthwhile because we're getting a lot of data in one go.
Right. And with each disk access, we're making significant progress either in our search or in modifying the data. And remember, the branching factor in B trees can be pretty big, like 50 to 2,000, because each node is optimized to fill up an entire disk block.
Wow, that's a lot of branching. So with one disk read, we could potentially be looking at hundreds or even thousands of directions to go in.
Exactly. And that's why the height of the tree stays so small. We just don't need that many levels to store a massive amount of data.
Makes sense. Now, the summary mentions some variations of the basic B tree. Can you give us a quick overview of those?
Sure. So we have the standard B tree, which is what we've been talking about. But there are a couple of interesting variations that are worth mentioning.
Okay, let's hear about them.
One is called the B plus tree, and it's actually super common. In a B plus P tree, all the actual data, like the stuff associated with each key, it's all stored in the leaf nodes.
Okay, so the actual data is only in the leaves. What about the internal nodes?
The internal nodes in a B plus tree, they just contain keys and pointers, no actual data.
Interesting. Why is that a good thing?
Well, it means the internal nodes can be packed even more densely with keys and pointers because they don't have to waste space storing the data itself.
So it makes the branching factor even larger.
Exactly. And that, in turn, makes the tree even shallower, which can mean even fewer disk accesses during searches. B plus D trees are super popular in database systems for this reason.
Okay, so B plus D trees are all about optimizing for those super fast searches. What about the other variation, the B tree? What's special about that one?
The B tree is all about space efficiency. In a regular B tree, remember we said the non-root nodes have to be at least half full.
Right, containing at least T1 keys.
Right. Well, a B tree is a bit stricter. It requires those internal nodes to be at least 2/3 full.
So they're packing in the keys more tightly.
Exactly. And that generally leads to better storage utilization, less wasted space. It can also reduce how often we need to split or merge nodes, which can be kind of expensive operations.
Okay, so it's a trade-off. B plus D trees prioritize speed, while B trees focus on space efficiency. Cool. Now let's go back to the standard B tree for a moment. The summary mentions a formula for the maximum height of a B tree. What does that tell us?
Sure. So for a B tree with n keys and a minimum degree of T, remember T has to be at least 2, the height of the tree can be no greater than locked n plus 1, 2.
Okay, that looks a bit mathy. What's the takeaway message here?
The key point is this. Even if you have a B tree with like billions of records, a really huge N, as long as you have a decent minimum degree T, the height of the tree is going to be surprisingly small.
So even with tons of data, the tree doesn't get super tall.
Right. And the reason for that is the logarithm in the formula. Because T can be pretty large in practice, that logarithm grows very slowly as N, the number of keys, increases.
So if I understand correctly, a regular binary search tree with millions of entries might be millions of levels deep. But a B tree with the same amount of data could be just a few levels deep.
Exactly. And the summary even points out that the height of a B tree is like LGET times smaller than a red-black tree with the same number of keys.
Wow, that's a big difference.
Yeah. And this dramatic reduction in height, that's why B trees are so good at minimizing disk accesses. We're just not traveling that far to get to the data we need.
Okay, the power of the large branching factor is really coming through here. All right, let's move on to the operations we can perform on a B tree. First up, searching. How does the B tree search algorithm work?
Okay, so searching in a B tree, it's kind of like searching in a binary search tree, but with a twist.
Okay, what's the twist?
In a binary search tree, at each node, you have 2 choices, left or right. But in a B tree, you could have many more choices.
Because of the higher branching factor.
Right. So we start at the root, and at each internal node, we scan through its keys to find the first key that's greater than or equal to the key we're looking for.
So we're doing a kind of linear scan within each node.
Yeah, it's a linear scan, but it's usually on a very small set of keys because each node is packed pretty densely. Anyway, if we find a key that's greater than or equal to our target key, we know the key we're looking for, if it exists, must be in the subtree to the left of that key.
Okay, so we follow the pointer before that key.
Right. And if our target key is bigger than all the keys in the current node, we just follow the rightmost pointer. And we just keep doing this, going down the tree until we either find the key or we reach a leaf node and realize it's not there.
Makes sense. It's like a more generalized version of binary search.
Exactly. And the summary mentions that this search operation, it accesses disk blocks, which makes sense because h is the height of the tree.
Right, so the number of disk reads is directly related to how tall the tree is.
Right, and the time the CPU spends doing the search, that's OTH, which is basically saying we might do a linear search in each of the H nodes we visit.
Okay, so that T factor is coming in because of the potential linear scans within the nodes.
Exactly. And it's important to remember that we usually assume the root node is always in RAM, so we don't have to do a disk read to get to it initially. And we also assume that any node passed to one of these B-tree procedures, it's already in RAM.
Okay, so those assumptions are just to simplify the analysis a bit.
Right, exactly.
Now, let's talk about creating a B tree from scratch. What happens in the B tree create operation?
That was pretty simple, actually. We just allocate a new block on the disk, which is like creating a new empty node.
Okay, so we're reserving some space on the disk for our new root node.
Right. And we initialize this new node as a leaf node, meaning it has no keys and no children. It's just an empty container for now.
Okay, empty and ready to go.
And finally, we write this new root node to the disk.
So we're saving it so we can find it later.
Exactly. And the cost of this whole creation process, it's just constant, O1
Yeah.
for the disk write and O1 for the CPU time to do the initialization.
Pretty straightforward. Now let's get into the more interesting stuff. Inserting a new key into the B tree. The summary mentions that B tree insert is more complex than in a binary search tree. Why is that?
The main reason is that with a B tree, we have to be really careful to maintain its structure. We can't just insert a key anywhere and call it a day.
Because we need to keep that balanced structure. Right?
Exactly. And one of the key things we have to watch out for is that no node gets too full. Remember we talked about full nodes?
Right, the ones with two T1 keys?
Yeah. If we try to insert a key into a node that's already full, it can mess up the whole B-tree structure.
So what do we do about that?
Well, the B-tree insertion algorithm, it uses this clever strategy called preemptive splitting.
Preemptive splitting, okay, what does that mean?
Basically, as we go down the tree to find the right spot to insert the new key, if we encounter a node that's full, we split it before continuing.
So we're like clearing a path as we go, making sure there's always space for the new key when we reach the correct leaf node.
Exactly. And by doing this preemptively, we avoid having to do more complicated restructuring operations later on. It keeps things much simpler.
Sounds pretty smart. Now, what exactly does this splitting involve? The summary mentions a procedure called B-tree split child.
Right, that's the key part. So imagine we had this internal node, call it X, and one of its children, let's call it Y, is full. So Y has two T1 keys.
Okay, so Y is packed to the max.
Right. What B-tree split child does is it takes this full child Y and splits it into two new nodes.
Okay, so we're dividing it in half.
Exactly. Each of the new nodes will have T1 keys. Now the middle key of the original child Y, that key, we move it up to the parent node X.
Okay, so the middle key gets promoted.
Exactly. And then we adjust the pointers in X so that the two new nodes, the ones we created from Y, they become children of X, sitting on either side of that promoted middle key.
So the middle key acts as a kind of pivot, splitting the child in half and going up to the parent.
Precisely. And this splitting process, it's the only way that the height of the B-tree can increase.
So the tree only grows taller when we have to split the root node.
Exactly.
Makes sense. Now, what's the cost of this splitting operation?
In terms of CPU time, it's T, which means it's proportional to the minimum degree T. It takes time to move the keys around and adjust the pointers.
And what about disk operations?
It's just O1. We only have to write the two newly created child nodes to the disk.
Okay, so the disk access is pretty minimal. Now, how does the overall B-tree insert procedure work?
Okay, so if the root of the B-tree is full, we first have to do a special kind of split. You can think of it as B-tree split root, even though it's not explicitly named that in the summary.
Okay, so a special case for the root.
Right. We create a new root node, make the old root its child, and then split that old root using the B-tree split child procedure we just talked about.
So we're basically pushing the old root down a level and creating a new root above it.
Exactly. And once we've done that initial split, or if the root wasn't full to begin with, we start going down the tree. And as we go down at each internal node, we check if any of its children are full.
And if we find a full child, we split it.
Right. We preemptively split it using B-tree split child before continuing down that path.
So we're always making sure that when we reach the correct leaf node, it's not full, and we have space to insert the new key.
Exactly. And once we reach the leaf node, we just insert the key in its proper sorted order, potentially shifting some existing keys to make room.
Sounds pretty efficient.
Yeah, it is. And the overall cost, it's O disk accesses because we're basically making one trip down the tree.
Right, one pass down to the right leaf node.
And the CPU time is OTH, which is proportional to both the minimum degree and the height of the tree.
Makes sense. Now, let's talk about the most complex operation, deleting a key from a B tree. The summary says that B tree delete is analogous to insertion, but even more complicated. Why is that?
Well, just like we have to make sure nodes don't get too full during insertion with deletion, we have to make sure they don't get too empty.
Because that could also mess up the B tree structure.
Exactly. Every node, except maybe the root, has to have at least T1 keys. That's the minimum. And if we delete a key in a way that violates that rule, we have to do some restructuring to fix it.
Okay, so it's about maintaining that minimum number of keys per node.
Right. And like insertion, B-tree delete tries to do this with a single downward pass. The goal is to make sure that any node we go into, it has at least T keys.
So we're being proactive again, making sure we have enough keys before we go further down the tree.
Exactly. Now, the summary outlines 3 main cases we have to consider, depending on where the key we want to delete is located.
Let's go through them.
Okay, so case 1 is the simplest. If the key K that we're trying to delete, if it's in a leaf node X, and that leaf node has more than the minimum number of keys, we can just delete it.
Okay, so if it's in a leaf node and it's not violating the minimum key rule, we're good to go.
Right. Now, case 2 is where things get a bit more tricky. This is when the key we want to delete is in an internal node.
Okay, so we're not at a leaf node anymore.
Right. And within case 2, there are a few subcases. Let's start with case 2A. If the child of the internal node that comes right before the key we want to delete, if that child has at least T keys, we can do something clever.
What do we do?
We find the predecessor of the key we want to delete.
Predecessor?
Yeah, the predecessor of a key is the largest key that's smaller than that key. So we find the predecessor within the subtree of that child node.
Okay, so we're looking in the subtree to the left of the key we want to delete.
Right. And once we find the predecessor, we recursively delete it.
So we're calling the delete operation on that predecessor key.
Yeah, exactly. And then, here's the trick. We replace the original key we wanted to delete with this predecessor key.
Okay, so we're swapping them out.
Right. And because the predecessor was the largest key in that left subtree, everything still stays in order.
So we've maintained the sorted order of the keys.
Exactly. Case 2B is similar. This time, we look at the child that comes right after the key we want to delete. If that child has at least 2 keys, we find the successor of the key we want to delete.
The successor is the smallest key that's larger than the key we're deleting.
Right. We find the successor in the right subtree, delete it recursively, and then replace the original key with this successor key.
So it's like we're borrowing a key from a neighboring subtree to take the place of the key we're deleting.
Yeah, that's a good way to think about it. Now, what happens if both of those neighboring children, the ones before and after the key, what if they both have the minimum number of keys, just T1?
That's case 2C, right?
Right. In that case, we have to merge things.
Okay, so we're combining nodes.
Exactly. We take the key we want to delete from the internal node, and we move it down into the left child. Then we take all the keys and pointers from the right child and move them into the left child as well.
So we're creating one big happy child node.
Right. And because we're merging nodes that had the minimum number of keys, the resulting merged node will have the maximum number of keys, which is 2T1.
So it's still a valid B tree node.
Exactly. And then we recursively delete the original key, which is now in the middle of this merged node from this new node.
Okay, so we merge and then recursively delete.
Right.
That covers case 2. What about case 3? That's when the key we want to delete isn't in the current internal node we're looking at.
Right. In case 3, we have to figure out which child node subtree might contain the key we're looking for. And if that child happens to have only T1 keys, which is the minimum, we have to be careful.
Because if we delete from that child, we might end up with too few keys.
Exactly. So in case 3A, we check if that child has a sibling that has at least 8 keys. If it does, we can do a redistribution.
Redistribution. What's that?
It's basically moving some keys around to balance things out. We take a key from the parent and move it down into the child that needs an extra key. Then we take a key from the sibling and move it up to the parent to replace the one that moved down.
Okay, so we're shuffling keys between the parent, the child, and the sibling.
Right. And we also move a corresponding child pointer from the sibling over to the child that's getting the extra key. This way, everyone ends up with at least the minimum number of keys.
It's like a little family loan to make sure everyone has enough.
Exactly. Now, in case 3B, if the child and all its siblings have the minimum number of keys, we have to merge again.
Just like in case 2C.
Right. We merge the child with one of its siblings, moving a key down from the parent to act as the median key in the merged node. And then we recursively delete the key from this merged node.
Okay, so merge if we can't redistribute. Got it.
And one more thing about merging. If the parent node happens to be the root of the tree, and after the merge it ends up with no keys, then the merged child becomes the new root.
So the tree can actually shrink in height during deletion.
Yeah, that can happen.
Okay, that was a lot of cases to consider. It's pretty complex, but it sounds like it's all about maintaining that balance and efficiency in the B tree. Now, what's the performance cost of all this?
Well, the good news is that despite all those cases, B-tree delete is still pretty efficient. It does ODisk operations, same as insertion and searching, and the CPU time is also OTH, which is proportional to both the minimum degree and the height of the tree.
Okay, so even though it's complicated, the performance is still in line with the other operations.
Exactly. The single pass down the tree and those local restructuring operations, the redistributions and merges, they help to keep the number of disk accesses under control.
Okay, so we've covered creating a B tree, inserting keys, deleting keys, and serving for keys. Sounds like we have a good grasp of the fundamentals. The summary.